Section 2.5, the chain rule. When we're considering the chain rule, it is when we have a composition of functions. I'm drawing a little diagram to help remind you about the composition of functions. The composition of functions is when you have a function that is defined at another function. So you see the value of x is inputted into the function g. G of x is the result, which then is inputted into the function f. When we look at the chain rule, when we try to take derivatives of composition of functions, the inner function would be the g of x, and the outer function would be the f of x. So when we are evaluating this derivative, we will take the derivative of the outer function, evaluated at the inner function, and then multiply that by the derivative of the inner function. We can look at this with Leibniz notation as well, which is right below. dy dx is dy du times du dx. So let's take a look at the first example. If we consider y being f of g of x, that would mean that g of x was x squared plus 1, and f of x, or we'll call it f of z, would be z cubed. So if I'm looking at y prime, I would have to take the derivative of the derivative of the outer, evaluated at the inner, times the derivative of the inner. So first let's consider the derivative of f would be 3z squared, and the derivative of g would be 2x. So when I'm taking f prime, I need to evaluate that at g of x. G of x is x squared plus 1. I would then need to multiply that by g prime of x, which is 2x. When I'm evaluating f, I see that it takes 3, or when I'm evaluating f prime, I notice that it's 3 times the input squared. The input happens to be x squared plus 1. I still have my 2x on the outside. I simplify, and I get 6x, quantity x squared plus 1 squared. And this is my derivative utilizing the chain rule. Let's take a look at another example. Y equals cosine 2x. In this case, y is f of g of x. It is a composition. And here, this is where your g of x would be the 2x, which g prime would be 2, and our f of x would be cosine, or we'll call it f of z, would be cosine z. F prime of z would then be negative sine z. So, utilizing the chain rule, y prime would be f prime evaluated at g times g prime. So I plug in my g of x, which is 2x, times my g prime, which is 2. Then f prime is the sign of the input, which happens to be 2x, and I still have the 2 on the outside. I then simplify, and my final answer is negative 2 sine 2x. When you look at the power rule combined with the chain rule, you'll look at example 3a, and it could have been calculated by taking n to be 3, so if you notice, example 1a could have been calculated by taking n to be 3. You don't necessarily have to follow the rule listed down at the bottom of the page. You can simply just do the chain rule and end up with the same answer. Let's do some more examples. If we take a look, we took the derivative of the outside, which is why I brought the 3 down, and took the power to the second. So this part right there is taking the derivative of the outer function. Now we need to evaluate that at the inner function. So I will write the inner function inside. Then I need to take the derivative of that inner function, which would be so I'm just writing derivative of the inner. The derivative of the inner would be 3 minus 4x. Then we simplify by rewriting all of that, and that would be our final answer. So let's take a look at letter B. Letter B has a quotient rule because it is the division that I highlighted in red. Also has a chain rule due to the denominator having a function inside of the square root. So quotient rule says leave the bottom derivative of the top minus leave the top derivative of the bottom. Now if I'm taking the derivative of the bottom, I need to use chain rule. So the 1/2 comes down, subtract 1 from the power, and I have negative 1/2. I evaluate that at the inner function, which is r squared plus 1, and then I multiply by the derivative of the inner function. All of this must be divided by the bottom function squared. And then we can simplify this a bit. And if we combine the two fractions on the numerator to form a common denominator, we will get this. And if we continue to simplify, the r squareds will go, and on the bottom we'd be left with that. That would be the final answer for the derivative. If we take a look at letter C, we have a chain rule situation because we have a function inside of a function. We also have a quotient rule due to the fraction that is inside. So first, we're going to take the derivative of g of t. So we will take the derivative of the outside chain rule. So we bring that 5 down, evaluated at the inner. So notice I brought the 5 down, changed the exponent to the 4, and now I need to evaluate that at the inner function, which is t squared over t plus 1. Then I'm going to need to multiply by the derivative of the inner function. For this, I will have to use quotient rule. Leave the bottom derivative of the top, minus leave the top derivative of the bottom, all over the bottom squared. Now then, it's just time to simplify. We continue to simplify, pulling out another t, and this is our final answer as the derivative of g of t. Let us do another example. If we look at letter D, we notice here that this is a product. So we will have to use the product rule. We also notice that there's a chain rule because we have the cube root, and we also have a function inside that cube root. So if we're taking the derivative of f, we will have to use the product rule. Derivative of the first, leave the second alone, plus leave the first alone, derivative of the second. Now when we take the derivative of the second, we will have to remember to use chain rule. So we bring down the 1/3, subtract 1 from the exponent, and that gives us an exponent of negative 2/3. We will evaluate this at the inner and then multiply by the derivative of the inner. Now then, it's time to simplify. I'm just rewriting that radical as a fractional exponent so that I can simplify it with the second piece. Notice that we have the x squared plus 2 and the x squared plus 2, which I underlined in gray. So if I pull out the 2x, so taking a look, that 2x is common to both. I took what I underlined in gray and just rewrote it in, and I broke it up so that I can see not only do both pieces have the 2x, but both pieces have an x squared plus 2 to the 1/3. So I'm going to factor out what I've highlighted in yellow, leaving us with the 1 plus and everything that was left. And that is the final, that is the final answer. You'll notice that the gray x squared plus 2 to the negative 1, you'll notice that it is now in the denominator because the exponent of negative 1. Moving on, the reason for the chain rule, or the reason it's called that, is because we can continue to take longer and longer chains, taking more and more derivatives. The idea is still take the derivative, evaluate it at the inner function, and then take the next derivative, evaluate it at the inner function, and keep going and going and going. So we can use the chain rule as many times as we needed. As many times as needed. So if we take a look at this, this actually has, let me rewind for just 1 second. This actually has 3 chains. 1 is the 3, 1 is the sign, and 1 is the 4x. So this is a case where we will have to do the chain rule twice. So f prime of x is equal to, so first we take the derivative of the outer. We deal with the 3 first. Bring the 3 down, take that exponent to 2, and then we're going to leave the inside the same. Then I'm going to take the derivative of the inside of the orange. That's cosine. I leave the inside the same, which is 4t, and then I take the derivative of that. Tried to color code it for you so that you can see you evaluate the derivative, leave the interior the same, and then take the derivative of that interior until you have nothing left. And then you just simplify. That becomes 12 sine squared of 4t cosine 4t. This is your final answer. If we take a look at letter B, again, we'll see that we have another 3. We have the squared, the cotangent, and the sine. So again, we will take the derivative. First we take the derivative of the 2, leaving us a 1 in the exponent. We will leave the interior the same. Then we will take a derivative of this interior, or of the red. Derivative of cotangent is negative cosecant. We will evaluate that at the inner function. Then we will take a derivative of the inner function again. which is negative cosine theta. And then we simplify, dealing with the negatives. We've got all of this left. That would be your final answer. And again, we can do this as many times as necessary. As long as there's a function within a function, you will continue to use the chain rule. This is the end of section 2.5.